This is part of the second floor of a two-story single-family residential building that is framed using sawn lumber. In this video, we will design the floor joists at the second floor. Our design will be based on the provisions in the International Building Code or IBC, which is adopted in nearly all jurisdictions in the United States. There are many states where the IBC is adopted with specific state amendments, but the wood design portion of the code is hardly significantly amended by any state and is therefore mostly adopted as provided in the IBC. The requirements for allowable stress design of wood are provided in Section 2306 of the IBC. The applicable standards for the design and construction of wood elements are provided in Table 2306.1. One of those standards is the National Design Specification for Wood Construction, also known as the NDS by the American Wood Council. This is the primary standard adopted by most engineers in the United States for the structural design of sawn lumber wood members. We will use the NDS standard in this example. The American Wood Council provides free access to view the NDS on their website. Please see the link in the description. Just like other construction materials, wood design may be accomplished using allowable stress design or the loads and resistance factor design methodology. For this example, we will use allowable stress design, which is arguably more popular for wood design than the loads and resistance factor design. The design process for wood joists using the allowable stress design involves the determination of the actual stresses due to the maximum loading required by the IBC. The designer also determines the allowable stresses based on the process described in the NDS. The adequacy of the joist is confirmed if it is determined that the actual stresses do not exceed the allowable stresses. In addition to the stresses, the designer must verify that the actual deflection due to loading does not exceed the allowable limits defined in the IBC. This video will demonstrate the complete design process for the sawn lumber joist that are supporting the second floor of a residential building. For this project, the floor joists at the second floor are spanning across the width of a building that is 15 feet wide. This is measured from the center of the exterior wall on one side to the center of the exterior wall on the other side. We will design the floor joists to span across the 15 feet width of the building. Let us begin by defining the loading. The loads on this project are based on the requirements in the International Building Code or the IBC. The loading requirements for buildings are provided in Chapter 16 of the IBC, where the different loads and load combinations are defined. For this analysis, we will consider the dead plus live load combination. First, let us evaluate the dead loads supported by the floor joists. Dead load is the actual weight of all the materials of construction, including fixed service equipment. The flooring on this project will consist of vinyl flooring over a 1/2-inch plywood subfloor. According to the Residential Structural Design Guide that is freely provided on the United States Department of Housing and Urban Development website, light frame floors such as the one we are considering will not exceed 10 pounds per square foot in weight. This is the dead load that we will use to design the floor joists. Please see the link in the description to access or download the Residential Structural Design Guide. Let us now consider live loads. The minimum live loads required for the design of structures are provided in Table 1607.1 of the IBC. The design live loads for single-family residential buildings are provided in Item 27 of the same table. According to Item 27, habitable attics and sleeping areas should be designed to support a minimum uniform live load of 30 pounds per square foot. All other areas should be designed to support a uniform live load of 40 pounds per square foot. Structural engineers typically use the 40 pounds per square foot uniform loading to design floor framing elements in residential building. This is the uniform live load that we will use in this example. As we mentioned, we will consider the dead plus live load combination. The total load based on this load combination is the sum of 10 pounds per square foot for dead load and 40 pounds per square foot for live load. The total load is 50 pounds per square foot. Therefore, we will design the floor joists to support a uniform load of 50 pounds per square foot. We will now commence with the selection of the floor joists. Before selecting the size and spacing, we need first to select the grade and species of lumber. For this design, we will use sawn lumber framing members. Sawn lumber species used in wood-framed construction in the United States are provided in Chapter 2 of the National Design Specification Supplement, which is another publication of the American Wood Council. Moving on, we will refer to this publication as the NDS Supplement. We will refer to the main National Design Specifications as the NDS. Just like the NDS, the American Wood Council also provides free access to the NDS Supplement on their website. A link to this publication is provided in the description. Some of the common lumber species used in residential wood framing include softwood species such as Douglas fir larch, hem fir, spruce pine fir, and southern pine. For each of these species, lumber comes in various grades. For this example, let us propose to use grade number 2 Douglas fir larch floor joists. Additionally, let us propose to use 2x10 joists that are spaced at 16 inches on center. Therefore, we will be verifying the adequacy of the 2x10 Doug fir floor joists. The design of uniformly loaded floor joists requires the evaluation of 4 critical elements. These include the bending stresses due to bending moments, the shear stresses due to shear forces, the bearing stress at the supports due to reactions at the supports, and the deflections, which are based on the stiffness of the floor joists. The floor joist must have adequate capacity in each of these considerations to ensure conformance with the requirements of the building code. In other words, the code requires that floor joists should have adequate capacity that exceeds the stresses due to bending moments, shear forces, and bearing forces, as well as adequate stiffness to prevent excessive deflections. We will begin by first determining the sectional properties of a 2x10 piece of lumber. Later on, we will use the sectional properties to determine the demand stresses and actual deflection. Sawn lumber framing members are specified using nominal dimensions. Nominal dimensions are different from the actual dimensions due to historical and processing reasons. It is a well-established tradition that lumber sizes are given in their nominal sizes. This is the size of the board before drying and planing smooth on all the 4 sides. According to the National Design Specification Supplement, a 2x4 piece of lumber should be no less than 1.5 inches by 3.5 inches, while a 2x10 should be no less than 1.5 inches by 9.25 inches. There are 3 important section properties that we need. First, the area is the product of the actual length and width. Therefore, the cross-sectional area is 13.88 square inches. We will use the area when evaluating the actual or demand shear stress. Secondly, the section modulus is the quotient of the product of the width and the square of the depth and 6. For a 2x10 that will be installed and loaded parallel to the depth of the joist, the section modulus is 21.39 cubic inches. We will use the section modulus to determine the maximum bending stress. Please note that if the 2x10 is installed as a plank such that it is loaded on the wider surface, the section modulus formula will consider the narrow dimension as the depth. Finally, the second moment of area or the area moment of inertia is the quotient of the product of the width and the cube of the depth and 12. For a 2x10, the second moment of area is 98.93 inches to the 4th power. We will use the area moment of inertia to determine the actual deflection due to the loading on the joist. Bending moments are the internal forces that cause a structural element like a joist to bend under applied transverse loads. These moments create a curvature in the beam resulting from compression and tensional forces across a cross-section. When a member is in bending as shown, the upper part of the beam experiences compressive force while the bottom part is in tension. The line between the tension section and the compression section is known as the neutral axis. Compressive force or compressive stress acting within the cross-section of the beam increase linearly from the neutral axis to a maximum stress at the top surface fibers. Similarly, tensile stresses increase linearly from the neutral axis to a maximum stress at the bottom surface fibers. Bending stress may be calculated using the bending stress formula that is provided in section 3.3.2 of the NDS. The bending stress is the quotient of the bending moment and the section modulus. Therefore, to calculate the maximum bending stress, we need to determine the maximum bending moment and divide this with the section modulus. The maximum moment of a uniformly loaded joist occurs at the midpoint. To determine the maximum bending moment on the uniformly loaded joist, we first need to determine the load supported by the joist. We already discussed that the joists will support 10 pounds per square foot dead load and 40 pounds per square foot live load, which sums up to 50 pounds per square foot at a spacing of 16 inches on center. This uniform area loading and joist spacing translates to a linear load of 67 pounds per linear foot after multiplying the uniform area load by the 16-inch or 1.333 foot spacing. The maximum moment is the quotient of the product of the uniform load by the square of the span and 8. The maximum moment is therefore 1,884.3 pounds-feet or 22,613 pounds-inch. We already determined that the section modulus is 21.39 cubic inches. The maximum bending stress is the quotient of the maximum moment and the section modulus. Therefore, the maximum bending stress is 22,613 pound-inches divided by 21.39 cubic inches. The maximum bending stress is 1,058 pounds per square inch. Therefore, the bending capacity of the joist needs to exceed this bending stress for the joist to be adequate in bending. In addition to bending moments, the floor joists will also have shear forces or shear stresses due to the uniformly distributed load. One of the most effective ways to visualize shear force is to assume that the joist is made up of layers that are arranged vertically as shown. Prior to loading, there are no forces acting between the layers. However, once the loading is applied, the layers begin to slip past each other with the maximum slip occurring at the supports. The force causing the layers to slip past each other is the shear force acting parallel to the longitudinal axis of the beam. Shear stresses parallel to grain may be calculated using the shear stress formula shown here. This formula is also provided in section 3.4.2 of the NDS, where it is provided in terms of the shear force. For rectangular wood beams and joists, the maximum shear stress is the product of 1.5 and the quotient of the shear force and the area. Therefore, in order to calculate the maximum shear stress, we need to calculate the maximum shear force. The maximum shear force on a member with a uniformly distributed load occurs at the supports. When calculating the maximum shear in this example, we will use the maximum shear at the supports. Please note that the National Design Specification allows maximum shear stress calculations to be based on the shear force at a distance equal to the depth of the beam away from the supports. According to section 3.4.2.2 of the NDS, the shear force induced in beams without notches or tapered cuts that are supported by full bearing on one surface and loading on the opposite surface may be determined by ignoring the uniformly distributed load within a distance from the supports that is equal to the depth of the bending member. Since shear increases as you move towards the supports for a member supporting uniformly distributed load, this allowance in the NDS will effectively reduce the shear force used to design such a member. This reduction is permitted because the loading within the distance equal to the depth of the member will be transferred to the support through bearing and will not contribute to the shear demand in the member. Typically, engineers do not apply this reduction when doing routine shear design calculations for long span members that are less likely to fail in shear. If we consider the full span for this project, the shear force is half of the product of the uniform linear load and the span. Therefore, the shear force is 503 pounds. Using the shear stress formula, the demand shear stress is 54 pounds per square inch, which means that the shear stress capacity of the joist should exceed 54 pounds per square inch. The other design consideration is bearing at the supports, which is also referred to as compression perpendicular to grain. The primary intent of this design consideration is to prevent unwanted deformation of the framing members at the supports or bearing locations resulting from crushing of the wood. According to Section 3.10.2 of the NDS, the compression stress perpendicular to grain should be less than the adjusted compressive design value perpendicular to grain. Let us first discuss what we mean when we say compression perpendicular to grain. If we consider the joist loading the top plates, the load is acting vertically downwards while the top plate grains are running parallel to the longitudinal axis of the top plates. Therefore, the loading is compressive and is acting perpendicular to the direction of the wood grains in the top plate. Similarly, if we consider the joist, the reaction is acting vertically upwards. On the other hand, the wood grains in the joists are running parallel to the longitudinal axis of the joists. Therefore, the loading is compressive and is perpendicular to the direction of the wood grains in the joist. The bearing stress is the quotient of the reaction and the contact area at the supports. Considering the 15-foot joist span and a total linear distributed load of 67 pounds per linear foot, the total reaction is half of the product of the uniform load and the span, since half the total load will go to each support. Therefore, the reaction is 503 pounds. Let us now look at the contact area at the supports. The top plates supporting the joists are 3.5 inches wide. The rim joist is 1.5 inches wide, which means that the bearing length of the joists is 2 inches. Since the joists are 1.5 inches wide, the contact area is the product of the bearing length and the width of the joist. The contact area is 3 inches wide. The bearing stress is the quotient of the reaction and the contact area. Since the reaction is 503 pounds and the contact area is 3 square inches, the bearing stress is 168 pounds per square inch. When checking bearing perpendicular to grain, we are concerned about the impact of bearing stress on both the joist and the top plates which are supporting the joist. The joist is experiencing this stress at the point of contact with the top plates, while the top plates are also experiencing this stress at the point of contact with the joist. For this example, we are assuming that both the top plates and joist are of the same species and grade, which means that the reference compression design value perpendicular to grain is the same. We have determined the maximum bending stress, shear stress, and bearing stress due to the loading supported by the joists. At this point, we need to determine the capacities of the joist with respect to resistance against bending stress, shear stress, and bearing stress. The first step involves determining design values that are known as the reference design values, which are provided in the NDS supplement. Please see the link in the description for free access to a copy of the NDS supplement that is provided on the American Wood Council's website. The reference design values for visually graded dimension lumber between 2 inches and 4 inches thick in nominal dimensions are provided in Table 4A of the NDS supplement. For grade number 2 Doug fir larch, the reference design values are as follows. The reference design value for bending is 900 pounds per square inch. The reference design value for shear is 180 pounds per square inch. The reference design value for compression perpendicular to grain is 625 pounds per square inch. The reference design value for the modulus of elasticity is 1,600,000 pounds per square inch. We will use this modulus of elasticity when calculating deflection. These are the reference design values that are based on normal load duration and dry service conditions. Section 4.3.1 requires the reference design values that we have determined to be multiplied by adjustment factors. Adjustment factors are used to modify the reference design values so that the final design value captures the local ambient conditions, loading and framing characteristics, and the specific structural attributes of the lumber element under consideration. The reference design values that we have determined are provided to accommodate a wide range of attributes, characteristics, and conditions, and may either not be adequate under certain extreme conditions or may be too conservative under certain circumstances. Therefore, adjustment factors are necessary to ensure that the capacity that is used in design reasonably captures the specific circumstances and ambient conditions that may affect or influence the capacity of a member. An adjustment factor may be less than 1, equal to 1, or greater than 1. Adjustment factors that are greater than 1 will increase the design value or capacity, while those that are less than 1 will reduce the design value or design capacity. Let us look at the adjustment factors that we need to consider in this project. The first adjustment factor that we will consider is the load duration factor. This factor is defined in Section 2.3.2 of the NDS. This factor captures the fact that wood has the property of carrying substantially greater maximum loads for short durations than for long durations of loading. The load duration factor for permanent dead load is 0.9. For occupancy live loads with a load duration of 10 years, the factor is 1.0. For snow loads at 2 months, the factor is 1.15, while the factor is 1.25 for construction loads with a load duration of 7 days. The 1.25 factor is normally applied when considering roof live loads. For seismic and wind loading with a load duration of 10 minutes, the factor is 1.6, while the factor is 2.0 for impact loads. According to the NDS in Section 2.3.2, the load duration factor for the shortest duration load in a combination of loads will apply for that combination. For this example, we are considering the dead plus live load combination. The load duration factor for dead load is 0.9 and the load duration factor for live load is 1.0. Since live load is estimated at 10 years and dead load is permanent, the duration for live load is less than dead load. Therefore, the applicable load duration factor for our design is 1.0. The next factor that we will consider is the temperature factor. This factor is defined in Section 2.3.3 of the NDS and captures the effects of elevated temperatures on the capacity of lumber. The effects depend on the reference design value being considered and the in-service moisture conditions. In all cases, for in-service temperature conditions that are less than 100 Fahrenheit, the adjustment factor for temperature is 1.0. While there are areas that temperatures will occasionally exceed 100 Fahrenheit in summer months, the decision to use a lower factor per the NDS or 1.0 for such areas is left to the engineer's judgment. For this example, we will use a temperature adjustment factor of 1.0. The next adjustment factor is the beam stability factor. The beam stability factor is denoted as CL and accounts for the reduced strength of a wood member under bending resulting from instability or lateral torsional buckling. When discussing bending, we said that for a simply supported member in bending due to downward loading, the top part of the member's cross-section is subjected to compressive stresses. If the compression zone is not laterally braced or laterally supported, the member may be subjected to sideways buckling that is characterized by lateral displacement and torsional twisting as shown in this cross-section. This sideways buckling occurs at a stress that is less than the design value provided in the NDS supplement. Therefore, to ensure that this is accounted for, the NDS requires designers to use a beam stability factor that is less than 1 where lateral torsional buckling is likely. For cases where a beam or joist is braced laterally, a beam stability factor of 1 is used, which means that lateral torsional buckling is unlikely to happen at stresses that are less than the design values provided in the NDS supplement. According to Section 3.3.2 of the NDS, when rectangular sawn lumber members are supported in accordance with Section 4.4.1 of the NDS, the beam stability factor is 1.0. Section 4.4.1 provides lateral restraint requirements for rectangular sawn lumber members based on their depth-to-breadth ratio based on nominal dimensions. We are using 2x10 joists, which means that the nominal depth-to-breadth ratio is the quotient of 10 and 2, which is 5. According to Section 4.4.1 of the NDS, for members with a depth-to-breadth ratio greater than 4 but not exceeding 5, the compression edge of the member shall be held in line for its entire length to prevent lateral displacement by adequate sheathing or subflooring. Additionally, the same section requires that the ends of the member at the point of bearing shall be held in position to prevent rotation and/or lateral displacement. For this example, 1/2 inch plywood sheathing will be applied above the floor joists and nailed to the floor joists. Additionally, the floor joists will be nailed to the rim joist to prevent lateral displacement or rotation at the supports as required by the IBC in Item 28 of the fastening schedule, which is Table 2304.10.2. Therefore, since our design has met the requirements provided in the NDS, we will use a beam stability factor of 1.0. The next adjustment factor is the bearing area factor, which is denoted as CB, which is used to adjust compression perpendicular to grain. The bearing area factor requirements for sawn lumber are provided in Section 3.10.4 of the NDS. The NDS allows bearing area factors that are greater than 1 for bearings that are less than 6 inches and not less than 3 inches from the end of a member. If we consider the top plates, we can see that the top plates will extend on both sides beyond the joist. Therefore, we can use a factor greater than 1 when considering the top plates. However, if we look at the joist, we can see that the top plate supports are provided at the ends of the joists and the joist does not extend beyond the top plate. Therefore, the bearing area factor is limited to 1.0 when considering the joists, which are also loaded perpendicular to grain by the reaction at the supports. Therefore, we will use a bearing area factor of 1.0. The other adjustment factor is the incising factor. Wood members that are preservative treated are generally incised, which involves making cuts on wood members that do not readily absorb preservative treatment to allow for the penetration of preservative treatment. The NDS in Section 4.3.8 requires the incising factors provided in this section to be used where dimension lumber is incised parallel to grain to a maximum depth of 0.4 inches, a maximum length of 3/8 inch and density of incision of up to 1,100 per square foot. Therefore, this factor is only applicable to lumber that is incised. Since we are not using preservative-treated joists, we will either ignore this factor or use an incising factor of 1.0. The next 4 factors that we will consider are defined in Section 4.3 of the NDS and provided in the NDS supplement at the section on Table 4A Adjustment Factors. Table 4A covers visually graded dimension lumber between 2 inches and 4 inches thick. The repetitive member factor, which is denoted as CR, is used to account for the increased load carrying capacity of wood members when they are part of a repetitive load system. For such members, a repetitive member factor of 1.15 may be used. The repetitive member factor applies to bending members that are used, such as joists, rafters, studs, planks, and decking that are spaced not more than 24 inches on center and are not less than 3 in number and are joined by a roof, floor, or other load distributing elements. Therefore, for this project, we will use a repetitive member factor of 1.15. The wet service factor, which is denoted as CM, accounts for the decrease in the strength and stiffness of wood when it is subjected to moisture. The reference design values provided in the NDS supplement are based on a moisture content of 19%. For cases where the moisture content will exceed 19% for an extended period of time, the NDS requires the application of the relevant wet service factor depending on the design value being considered. For this project, the floor joists will not be exposed to moisture and therefore we will use a wet service factor of 1. The next factor is the size factor, which is denoted as CF. The size factors are also tabulated in the NDS supplement at the section on Table 4A Adjustment Factors. Size factors vary by size and the design value being considered. For a Grade 2 joist that is 2 by 10 in nominal dimensions, the size factor for bending is 1.1. Therefore, we will use a size factor of 1.1. Finally, the last factor is the flat use factor. This is applicable for cases where framing members are framed such that the load is applied to the wide face, such as a plank. This is obviously not applicable for this example since joists are framed such that the loading will be applied to the narrow face of the joist. Therefore, we will use an adjustment factor of 1.0. We have discussed and determined the applicable adjustment factors. The next step is to calculate the adjusted design values. Let us start with the adjusted bending design value. According to Table 4.3.1 of the NDS, the adjusted bending design value based on the allowable stress design methodology is the product of the reference design bending value and the load duration factor, the wet service factor, the temperature factor, the beam stability factor, the size factor, the flat use factor, the incising factor, and the repetitive member factor. Please recall that we are using the allowable stress design methodology, which means that we are using adjustment factors that are associated with allowable stress design. We had previously determined that the reference design value for bending for grade number 2 Douglas fir larch lumber is 900 pounds per square inch. We have also determined that all of these adjustment factors are 1.0 except the size factor, which is 1.1 for the 2 by 10 sawn lumber joists, and the repetitive member factor, which we determined is 1.15. Therefore, the adjusted bending design value is 1,139 pounds per square inch. This is greater than the actual demand bending stress of 1,058 pounds per square inch, which we determined is the maximum design bending stress based on the loading. This means that the joist is adequate in bending. It is customary for engineers to represent this comparison as a ratio known as a unity check, which should not exceed 1.0. This is done by dividing the actual stress by the adjusted reference design value. In this case, the unity check is 0.93, which means that the joist is 93% stressed and has about 7% of residual capacity. The unity check is very helpful when comparing the relative adequacy of different members in a system. The designer can easily see the strongest and weakest member in a system of elements supporting loading from the same source or different sources. Let us now check shear. The applicable adjustment factors that are required for the determination of the adjusted shear design value are also provided in Table 4.3.1 of the NDS. Please recall that we are using the allowable stress design methodology, which means we will only use the adjustment factors that are associated with allowable stress design. According to the NDS, the adjusted shear design value based on the allowable stress design methodology is the product of the reference design shear value and the load duration factor, the wet service factor, and the incising factor only. We had previously determined that the reference design value for shear for grade number 2 Douglas fir larch lumber is 180 pounds per square inch. We have also determined that the load duration factor, the wet service factor, and the incising factor are all 1.0. Therefore, the adjusted shear design value is 180 pounds per square inch. This is greater than the actual demand shear stress of 54 pounds per square inch, which we determined was the maximum design shear stress based on the loading. The unity check is 0.3, meaning that the joist is only 30% stressed in shear. This means that the joist is adequate in shear. Having checked bending and shear, we still need to check bearing at the supports. According to Table 4.3.1 of the NDS, the adjusted compression design value perpendicular to grain based on the allowable stress design methodology is the product of the reference design value for compression perpendicular to grain and the wet service factor, the temperature factor, the incising factor, and the bearing area factor. We had previously determined that the reference compression design value perpendicular to grain for grade number 2 Douglas fir larch lumber is 625 pounds per square inch. We have also determined that the wet service factor, the temperature factor, the incising factor and the bearing area factor are all 1.0. Therefore, the compression design value perpendicular to grain is 625 pounds per square inch. This is greater than the actual demand compressive stress perpendicular to grain of 168 pounds per square inch, which we determined was the maximum compressive stress at the supports based on the loading. The unity check is 0.27, meaning that the joist and supports are only 27% stressed in compression perpendicular to grain. This means that the joist and top plates are adequate in compression perpendicular to grain. We have checked the joist against bearing, bending and shear demands and have found that the joist is adequate. The next consideration is deflection. Deflection is a serviceability concern, which means that the check is intended to prevent excessive deflection which may compromise the ability of the joist to provide useful service. Excessive deflections may lead to cracking of rigid finishes and compromise the aesthetic value of the system. The total amount of deflection for a beam in bending may be broken down into two components. First, there is the bending deflection component, which is associated with the bending stiffness of a member, and then there is shear deflection component, which is associated with the shear stiffness of a member. According to Section 3.5.1 of the NDS, in conjunction with Appendix F of the same NDS, the modulus of elasticity used to calculate deflection for visually graded dimension lumber already includes the shear deflection component. Therefore, the shear deflection component is included in the final deflection based on bending deflection equations. Bending deflection depends on the modulus of elasticity, which is a material property, and the second moment of area or the area moment of inertia, which is a property of the cross-section of a member. We already determined the area moment of inertia and have also determined the reference design value for the modulus of elasticity. Therefore, at this point, we need to determine the adjusted design value for the modulus of elasticity so that we can use it to calculate the deflections. According to Table 4.3.1 of the NDS, the adjusted design value for the modulus of elasticity is the product of the reference design value for the modulus of elasticity and the wet service factor, the temperature factor and the incising factor. We had previously determined that the reference design value for the modulus of elasticity for grade number 2 Douglas fir larch lumber is 1,600,000 pounds per square inch. We have also determined that the wet service factor, the temperature factor and the incising factor are all 1.0. Therefore, the adjusted design value for the modulus of elasticity is 1,600,000 pounds per square inch. This is the value that we will use in our deflection calculations. When a uniformly distributed load such as the one we are considering in this example is applied on a member, the maximum deflection occurs at the mid-span of the member. The maximum deflection is the quotient of the product of 5 and the uniform load and the fourth power of the span over the product of 384, the elastic modulus and the area moment of inertia. For deflection, the IBC code requires that we check two deflection limits on Table 1604.3, which is provided in Chapter 16 of the IBC. There are actually three deflection limits, which include the limit when considering live loads only, the limit when considering wind or snow loads, and the limit when considering dead plus live load. Since we do not have wind or snow loads in this example, we will only consider the live load limit, which in this case is the span over 360, and the dead plus live load limit, which is the span over 240. Let us start with the live load limit. The live load limit is L over 360. L is the span, which means that the maximum allowed live load deflection for this project is 15 feet times 12 inches per foot over 360. This is 0.5 inches. This means that when considering live load only, the deflection should not exceed 0.5 inches. Let us now calculate the actual live load deflection. We will express all factors using pounds and inches for consistency. Since the uniform live load is 40 pounds per square foot and the tributary width of each joist is 16 inches or 1.33 feet, the linear uniformly distributed load is 40 times 1.33 feet. Therefore, the linear uniformly distributed load is 53.33 pounds per linear foot. This may be converted to pounds per linear inch by dividing by 12 inches since there are 12 inches in 1 foot. Therefore, the loading is 4.44 pounds per linear inch. The span of the joist is 15 feet. This is equal to 15 by 12 inches per foot, which is 180 inches. We have already determined that the modulus of elasticity is 1,600,000 pounds per square inch and the area moment of inertia is 98.93 inches to the fourth power. Therefore, the live load deflection is 0.38 inches. This is less than the maximum 0.5 inch limit that we have determined, and therefore the joist is adequate. Finally, let us now look at the long-term deflection limit. According to Table 1604.3 in Chapter 16 of the IBC Code, the dead plus live load limit is L/240. Since the span is 15 feet, the deflection limit in inches will be the quotient of the product of 15 feet and 12 inches per foot and 240, which is 0.75 inches. Table 1604.3 also includes footnotes with important information about the dead plus live load combination. According to footnote D of the same table, the dead plus live load combination applies to the creep component of long-term dead load deflection plus short-term live load deflection. The footnote goes on to say that for lumber members that are dry at the time of installation and used under dry conditions, the creep component of long-term deflection shall be permitted to be estimated as the immediate dead load deflection resulting from half the dead load. This means that the code allows a load combination of 0.5 dead plus live load to be used instead of dead plus live load. For this example, we will be conservative and use the full dead load. According to Section 3.5.2 of the NDS, the total deflection under long-term loading consists of two components. The first component is the product of the creep factor and the immediate deflection due to the long-term component of the design load. This means that the first part is the product of the creep factor and deflection due to the dead load. The second component is the deflection due to the live load. We have already calculated the deflection due to the live load. Therefore, we will calculate the deflection due to the dead load and multiply the deflection with the creep factor, which according to the NDS is 1.5 for seasoned lumber used in dry service conditions. The uniform dead load is 10 pounds per square foot. The uniform linear dead load is the product of 10 pounds and the tributary width, which is 1.33 feet. Therefore, the uniform linear dead load is 13.33 pounds per linear foot. This may be converted to pounds per linear inch by dividing by 12 inches since there are 12 inches in 1 foot. Therefore, the loading is 1.11 pounds per linear inch. If we use the deflection formula, the dead load deflection is 0.096. The total long-term deflection is the sum of the product of 1.5, which is the creep factor, and the 0.096 dead load deflection plus the live load deflection of 0.383. The total long-term deflection is 0.527 inches. This is less than the maximum 0.75 inches limit for dead plus live load deflection, and therefore the joist is adequate. We have completed the design of the floor joists and have determined that it is adequate. If you enjoyed this video, don't forget to give it a thumbs up and subscribe to the channel, and do not forget to hit the notification bell so you never miss an update. Your support helps us keep creating great content, and we'd love to have you join the community. Thank you for watching.